All right, physicists, welcome to our January 13th edition of physics. This is our very first recorded talk. I apologize for the visuals on myself. You'll notice that behind me, the Venetian blind in my office has fallen down, so it looks like I'm podcasting from the surface of the sun. I don't think you're probably looking too carefully at this screen anyway. So, hello, my name is Dr. Cordall. Today we're going to be talking about two things. One, procedural stuff. We're going to be talking about how this course is run. So if you are interested in getting an A in the course, this is the time to listen. And two, physics stuff. And that's basically just unit conversions, how to go from feet to meters, and feet squared to meters squared, that sort of thing. Okay, so briefly, I recommend that you take a look at your syllabus. It is on Canvas. And in your syllabus, there's a list of the main topics we're going to study in Physics 105. And depending on how much physics you've already taken, this might look like a lot or it might look like a little. So for instance, we're going to cover basic physical quantities, vectors, velocities, acceleration, force, energy, momentum, angular momentum, energy conservation, conservation of momentum, conservation of angular momentum, Newton's law of universal gravitation, heat, temperature, all that type of stuff. So these are pretty classical topics. And if you haven't covered them before, you're in for a treat. If you have, hang around anyway, because my only warning about physics is that it's the sort of course where you can feel like it's very easy until it's not. So hopefully you can stay on top of every topic as we go along. If you are feeling that you're missing something, that there's something that doesn't make sense about it, that's a good time to immediately start coming to office hours. And so I'm around pretty much every afternoon, and I very much welcome people to stop by or schedule a Zoom call or whatever, because it's much better that you come early, come often, rather than waiting and hoping that it gets better. So let's look at what does a normal week of physics look like. So the first thing I want to do is shift our expectations a little bit. Your class listing, I believe, has a long period on Monday, a long period on Wednesday, and then a shorty period on Friday. And what I want us to try to aim for is to have about a 50-minute period on each one of those days. And on Monday, Wednesday, it's going to start at 9:30, and on Friday, it's going to start at 10. And basically, my reason for that is, it is the era of COVID, so I'm not supposed to have students working together in groups. If it is just me talking mostly, and listening to someone for more than 50 minutes is a lot. In fact, I find that after 40 minutes, people are pretty tired of hearing me talk. So let's just try this. If it doesn't work, we can always reassess that as the semester goes on. So every week you're going to have a quiz or a test, and that'll be taken on Friday, and you'll have a homework set due, and that'll be due on Monday. And so last semester, when I was teaching Physics 2, I tried to have both homework and quizzes on Fridays. And what I found is that people put off their homework sets until it's due. And so I really want to encourage you not to do that. A lot of people would be putting it off and then trying to get it done on Friday, and then end up handing it on a Saturday or Sunday. So what I want to encourage you to do is aim for getting it done on Friday. If you want to hand it in on Friday, great, I'll take it. And then the real, deadline after which, you'll be counted late and you'll get half credit for it, will be Monday. So please get your homework in on Mondays. And then on Fridays, I'll try to make that period even a little shorter than 50 minutes, because every Friday I'm going to be putting an online quiz on Canvas. And that online quiz is going to actually be open book. So that is not intended as a punishment. It's hopefully just a way for you to make sure that you're caught up with the material. And as I said, office hours pretty much every day. On Thursday, I have a lab with my other course, Modern Physics. But other than that, feel free to stop by. Feel free to schedule a Zoom call with me, because I really want to make sure that you're keeping up to date on our topics. Oops. All right, now, something that every professor should talk about on the first day of class is how to succeed in the class. Now, the way I've set up the course is such that I think it's a little bit hard to fail it if you're doing all the work. And it's a little bit hard to get an A unless you're really mastering the material. And that's sort of by design. I think that it's my job as your professor to make sure that you're going to pass the course, hopefully get a C or above. But it's not my job to get you an A. That's your achievement. So how is that going to be possible? Well, one thing I notice here is that 45% of your grade is just you showing up and doing the work. So 25% is homework. Homework is you handing in your problem sets. If you want to hand those in online, that's also fine. If you want to scan in your work and give it to me that way, that's okay. However, this part, I'm not going to go and grade you on, is it right? I'm going to grade it on, did you do the whole thing? Did you get an answer? Did you put some units on it? So that's what I'm looking for. You don't need to necessarily master the material fully to get that 25%. I'm looking for that you do it. And I'll be posting answer sets, and I really want you to do well on that. As well, 5% here is just participation. Okay, so that's showing up to class. On the in addition, quizzes here are 15%. So those, as I said, they are based on getting the right answer. But you can use your textbook. You can take time. You may not use your neighbor. They are by yourself activities. Homework, I encourage you to work together with your friends as much as you can. But quizzes are another way to sweat your way to success. On the other hand, look, we've got 40% for the regular tests during the semester. That's three tests, and then your final exam is another 15%. So that part is based on how well you do on the test. And I'll be giving you review sheets, and hopefully when you get to the test, it won't be a surprise what's on there. But you do have to master the material. And so I guess I should say for the tests as well, my goal is for you to pass the course and not waste all the money that you're paying to Centenary. And so if let's say you really bomb a test, you get a 40% on it, I will provide ways for you to do test corrections and get that up to a 60%. I will not provide a way for you to get, a 90%. And so this grading scale, you should take this seriously. This is what I'm going to go off of. It won't be it won't be further curved. I've built in enough points here that you should be able to hit the grade that you're looking to get. Okay, so as I say, anything that I say in this video that seems confusing or what does he really mean, try reading the syllabus. If it's not in the syllabus, just shoot me an email and I will try to get back to you ASAP. All right, now today our basic concern is thinking about units. And let's say, as we do in physics, that we want to reduce our description of the world to be quantitative. We want to use numbers to describe the world. How can we make it so that everyone understands what we mean? Well, what we usually do in physics is to use some conventions. And by conventions, I mean you have some standard, and the standard is made up. It doesn't mean anything until you say what it is. So for instance, back in the day, mass of a kilogram was defined as just the mass of whatever this hunk of metal was in Paris. And the length of a meter was defined as whatever this length of this metal post was in Paris. And for time, this is a little bit more of a complicated one, but if you go back long enough, the idea was that you take a pendulum and it swings one way, that's 1 second, another way, that's another second, and the length of the pendulum was 1 meter long, and that pendulum was held, guess where, in Paris. Okay, just checking to make sure that I'm recording. Now, as you can probably see, there's going to be problems with this. So, for instance, if you're defining your kilogram in terms of a piece of metal, what happens if the metal rusts? What happens if it oxidizes on the surface? Then it's going to get heavier. Does that change the mass of everything else in the world? And then what about your meter stick? When it gets hot, it expands a bit. When it gets cold, it shrinks down a bit. What about that? And furthermore, with your pendulum, that changes a little bit depending on what time of year it is, depending on where on Earth it is, the elevation. That'll change the period of the pendulum. So really, the process of removing these ambiguities takes a lot of work. And if you go on Wikipedia, and I actually recommend this, and go and read the article "History of the Meter," you'll find that it's a very long article because there's been a lot of people trying to think about how you can hammer down length. And that's, as ideas about physics change, ideas about how you should talk about length change. And so all of these things, it's kind of, a snake chasing its own tail type of exercise. On the other hand, we don't need to worry about all of that. Basically, in this course, the depth to which we need to think about units is the problem of different prefixes, kilo, hecto, deca, deci, centi, milli, micro, nano, pico. So that's really from about tera to pico. Those are the ones that I know well, maybe femto. But then the really small ones and really big ones I probably would have to look up. And then for different base units, to be honest, I don't remember a lot of these types of conversion factors. I remember 1 inch is 2.54 centimeters. That's the one that I remember, and then I can usually get between things that I need to go between. But let's see the basic process. So there's one. So all I'm saying in this slide is, don't waste your time memorizing this stuff. I'll give it to you. I'll give you this on a page for your tests. Now, the method, though, this is something you should know. And the solution to changing between one type of unit, from feet to meters, or inches to centimeters, or whatever you have, here we have minutes to seconds, is that you can always multiply things by 1, and that's never wrong. So for instance, if I have 1 minute equals 60 seconds, all right, I can go ahead and divide both sides of that by 60 seconds, right? And that gives me that 1 minute over 60 seconds is just the number 1. This doesn't have any units. So for instance, if I wanted to do something silly and say, I want to express 4 pounds as 4 pound minutes over 60 seconds, those are equal. It's very silly. You wouldn't do it, but it's not wrong. And so what that helps us with is that we can always multiply by 1. And so for instance, let's say we had a quantity like 2 minutes. 2 minutes is the length of time. We can use different forms of 1 to convert that to different types of expressions for a second. So here we have 2 minutes times 1. And we call this the train track method because I'm going to write my fractions so they look like train tracks. And I want to have minutes so they cancel out. So I'm going to put 1 minute over and then 60 seconds over that. Now, what did I do here? I'm taking 2 times 60 over 1. This is just another way to write 1. So 2 times 1 is still fine. But what I can do now is that I have minutes on the bottom, minutes on the top, and those units can cancel out. So that's the worst written 1 that I've ever drawn. There's a 1. Okay, 2 times 60 is 120 seconds. Okay, so that's the basic method, and that's really the only idea of today's class. However, as always, there are subtleties. So for instance, here's an example from your homework. Horses are set to race over a certain English meadow for a distance of 4 furlongs. What is the race distance in rods or chains? Well, okay, let's try part A. It says 1 furlong is 2.01 times 0.168 meters, and 1 rod is meters. So what we're basically going to be doing here is our train track method. So let me put a train track. I start out with a distance of 4 furlongs. Okay, so 4 furlongs. And I want to get that in terms of chains. Or, sorry, let's just do rods. I want to do this in terms of rods. So, do I have a conversion factor of furlongs to rods? I do not. However, I have a conversion factor of furlongs to meters. And then I'm going to have another conversion factor of meters to rods. Okay, so furlongs to meters, I want to have this factor right here be 1. So 1 furlong is 201.168 meters. And then if I want to go from meters to rods, I also want this factor just to be 1. 1 rod is 5.0292 meters. Okay, so the furlongs cancel, meters cancel, and this should give me a number in terms of rods. 4 times 201 divided times 1 divided by 1 divided by 5.292 gives me a number of rods. Okay, so as you'll see, you can do the conversion to chains. This method is going to use a couple of train tracks. You have to multiply by 1 You can multiply by 1 again. You can keep doing that for a while. And it's never wrong because you're just multiplying by 1. Now, let's think about it. What happens when you're doing this with hybrid units? Now, what do I mean by a hybrid unit? I mean something that involves more copies. So for instance, area is a length times a length. Or volume is a length times a length times a length. Now it turns out that you have to convert each one of those units. You don't just get to convert one of them, you have to convert each one of those lengths. So let's look at an example of this. So let's consider 1 mile is 5,280 feet. So I can always write 1 equals 1 mile over 5,280 feet, okay? Now, if I have 2,000 feet, I can just use my train track method and convert that to miles. So I would go 5,280 feet, 1 mile equals. Okay, so just take 2,000 divided by 5,280, you'd find something a little bit less than a half, and your feet would cancel out. It would give you an answer in terms of miles. However, what if you had 2,000 feet squared as an area? Well, in that case, 2,000 feet squared is 2,000 feet times feet. Okay, so that is not the same as 2,000 feet by 2,000 feet. It's something different. And so in this case, you'd have to go 1 mile over 5,280 feet, and then go 1 mile over 5,280 feet. So essentially, you need to square this 1. So you need to take 2,000 feet squared times 1 squared, and that gives you your answer in miles squared. Okay, so in this case, one of these factors would cancel out one of the feet, the other one would cancel out the other one. Okay, so you have 2,000 divided by 5,280 divided by 5,280, and that would give you your new number in terms of miles squared. So I gave you one homework problem. This would be a sort of a stupid way to do it because it says Earth is approximately a sphere of radius 6.37 times 10 to the 6 meters. What are its circumference in kilometers, its surface area in square kilometers, and its volume in cubic kilometers? Well, what you should do in this problem is convert this into kilometers and then just use your circle and sphere formulas. I do give you these, though, because I noticed that people don't always have these in their back pocket the way that I think they should. So here's the distance around this, the circumference is 2 pi r. The area of this is pi r squared. The surface area of a sphere is 4 pi times r squared. You probably calculated that in calculus at some point, I would imagine. And I think in calculus you probably also calculated 4/3 pi r cubed for the volume of the sphere. Now, the other reason that I put this example in here is to call attention to something, which is, let's say that you have r equals 6.37 times 10 to the 6th meters. All right? I think everyone, I hope, knows what this means. The 10 to the 6th means you have 0.37, and you need to move over the 0 6 places. 1, 2, 3, 4, 5, 6. 0, 0, 0, 0. Okay, and writing that out is a big pain and a bother. So that 6,370,000, which is the same number here, it's easier to write it out in scientific notation. However, the thing to keep in mind is if you have r squared, okay, 6.37 times 10 to the 6th squared means that you're doing 6.37 times 10 to the 6th times 6.37 times 10 to the 6th. And then if this is meters, that would give you a meters squared. And so when you're squaring something that's in scientific notation, it would be 6.37 squared times 10 to the 6th times 10 to the 6th. 6 plus 6 gives you 10 to the 12th. Okay, so be very careful when you're doing that. If you're just plugging this into your calculator and put something like 6.37 E6 squared, make sure that you're putting in the parentheses so you're not getting yourself confused. Okay, so this should be something around 36 E12, so somewhere around there. Here's an even more complicated homework problem. If you have hydraulic engineers in the United States, will often use as a unit of volume of water the acre-foot, defined as the volume of water that will cover 1 acre of land to a depth of 1 foot. A severe thunderstorm dumped 2.0 inches of rain in 30 minutes on a town of area 26 kilometers squared. What volume of water in acre-feet fell on the town? Okay, so remember, volume is length times length times length. Or in this case, it's going to be area times length. So in this case, notice they give you this is very common in problems like this. They give you a little bit of flarf. This is part of the problem that you don't need. This 30 minutes, that is extra information that they put in there to confuse you. The volume that you start out with is 26 kilometers squared, that's the area, times a height, which is the 2 inches. Okay, so I'll tell you the way I did it. When I did this problem, I converted all my quantities into cubic meters. So I know how to do kilometers into meters. So you need kilometers to meters, kilometers to meters. I knew how to go from inches to centimeters, centimeters into meters. So that gave me my whole volume in meters cubed. And then once I knew how to get it into meters cubed, I could go and convert it into rods and furlongs. 1 rod by 1 furlong is 1 acre. And then I could convert from meters back into feet. But that's not probably the most efficient way to do it. You can go and look up whatever conversion factors you like in the appendix to your book, and go nuts with your train tracks. So this is a more complicated example, but that is often how things are out in the world. You're not given the units that you would like. You have to take the information as it's given. Okay, well, of course, there's other ways that we can combine units. An example of a hybrid type of unit that's a little bit more tricky than even meters squared, because those are both lengths, is something like density, which has mass on the top and volume on the bottom. It's how much stuff there is per unit of space. But the idea is the same as before. To transfer units, we're going to just multiply by 1 as many times as we need to. So a good example is, how would we do 15 grams per inch cubed? This is a mass. This is a volume. we have to, at the end, have some units that are a mass over a volume as well. Well, what would we do to get grams to kilograms? Well, 1,000 grams equals 1 kilogram. Okay, so we can use that to go from grams to kilogram. 12 inches is 1 foot. Okay, so it's easy to see how we're going to make a factor of 1 with this. It's easy to see how we're going to make a factor of 1 with that. We just need to be careful that when we do our transformations, we are respecting both the position of the units and the fact that there are 3 copies of inches. So, for instance, here we have 15 grams per inch cube. To convert that at the end of the day into something that's kilograms over feet cubed, some number, we need to go from grams to kilograms. So grams, kilograms, 1,000 grams is 1 kilogram. Okay, so that's multiplying by one time. And then for each one of these, this is really inches times inches times inches, we're going to need a factor of 12 inch times 1 foot. Now, you could just write that cubed, but just to be really explicit, I'm going to write it out 3 times. 12 inches, 1 foot. 12 inches, 1 foot. 12 inches, 1 foot. Okay, so inch cubed goes with inches times inches times inches, and here we have feet cubed. So we have kilograms over feet cubed. All right, so as I say, a little tedious, but hopefully not hard. You're just multiplying by 1 over and over and over again. Here's a problem that is a little tricky. It's mostly because they want you to think about rates and converting, something that starts out as a volume into a mass into a time. Okay, so let's read the question. The record for the largest glass bottle was set in 1992 by a team in Millville, New Jersey. Here it is. I looked it up on Facebook. They blew a bottle with a volume of 193 U.S. fluid gallons. How much short of 1.0 million cubic centimeters is that? And if the bottle were filled with water at the leisurely rate of 1.8 grams per minute, how long would the filling take? Water has a density of 1,000 kilograms per meter squared. Okay, so what sort of things are we going to do? Well, in part A of this problem, it basically it's asking us just to find this volume. So it's 193 gallons, and we can go from gallons to cubic inches. Whoops. Gallons on the bottom, cubic inches on the top. And then we can go from inches cubed to centimeters. Here I give you a factor, 1 inch. And then you're going to have to cube that thing because it's got to go inches times inches times inches to cancel out those, and then centimeters times centimeters times centimeters. Okay, so then you would have gallons per, or you'd have the volume in cubic inches. Now, for part B, they're asking you something different. If the bottle was filled with water at the leisurely rate of 1 gram per minute. So they're saying, look, the density is known. They give you the density in kilograms per meter squared. And that is the mass divided by the volume. So if you want, you can go ahead and find the mass of water that would fill up the the bottle. Okay, so you're going to find the mass of water that fills up the bottle. Now, then they give you a rate, which is a mass over a time. And then they ask how long would it take. So they essentially want you to take the rate. So I'm going to do a little bit of fanciness here. You can do the algebra. Rate times time equals mass. Mass over the rate. So essentially, yeah, it takes quite a few train tracks to get everything straight in this problem. It's a little tricky. Give it a shot. If we want to put in take a little more time to look at it on Friday, I'm willing to do that again. But please take some time and try to get it on your own, because I don't know if it's worth me going through all the factors in a video, or if you can see how it's going to work. Okay, now one last thing, and then we can be done with this video. Precision versus accuracy. You probably have seen this cartoon before. This is not very accurate because the shots are all over the place. It's not very precise because they're not clumped. This one is both accurate and precise because all of the shots are clumped in one place, and they're they're accurate but not very precise because the shots are basically around the bullseye, but they're a bit spread out, so the precision is low. Here you have accuracy low. It's not hitting in the bullseye, but it is. The shots are all around the same area. And here the accuracy is high because they're in the right place, and the precision is right because they're all in the same place. So this week with Dr. Galaba, I believe you're going to do a lab talking about precision and significant figures and stuff like that, so I'm not going to harp on it too much today. By the way, your lab grade is separate from the grade that I give you in this class, so whatever Dr. Galaba says over there is law, so please ask him separately, because he gives you a grade and I give you a grade, and those two scores are not necessarily coupled. So for significant figures, it's all about not overstating the precision of your knowledge. So we measure something, and in this course, when you're going to calculate, for instance, from measurements of volume and measurements of mass, you're going to calculate something like the density. You want to make sure that you're not overstating how much you know about the density. And essentially, whatever factor in your equation you know the least about is what controls your knowledge. So when you're multiplying or dividing, we respect the term with the fewest digits. So for instance, if we have a long number like this, and we're multiplying two numbers together, this has lots of digits. 1, 2, 3, 4, 5, 6, 7, 8. Okay, well, this is pi. This, on the other hand, only has 2 digits, so I don't get to say 13 point something here. In fact, I only get 2 significant digits, so I just get the 2 there. I don't get to say anything beyond the decimal point. Similarly, when you're adding or subtracting, you respect the term with the fewest decimal places. So this is lots of decimal places. When you add, you don't get to say anything about all of that because you don't know if this is 2.40000 or 2.4, 4527, blah blah blah. So the way that we respect that is by lopping off all of the stuff that's unnecessary. I will say, however, when you're doing calculations, it never hurts to keep the digits around until you report the final answer. And this is something I see students do wrong quite a bit. Is, let's say that you have a multi-step problem, it's a good practice not to throw away any of those digits until the very end of the problem, because you don't want to introduce extra errors by rounding that you could avoid, you know, and so just lop off the digits at the very end when the time comes. All right, I did give you one problem in your homework that's sort of asking you to do a guesstimate. So it says a mole of atoms is 6.2 times 10 to the 23rd atoms. To the nearest order of magnitude, how many moles of atoms are in a large domestic cat? The masses of a hydrogen atom are an oxygen atom, a carbon atom are 1 atomic mass unit, 16 atomic mass units, and 12 atomic mass units, respectively. Hint, cats are sometimes known to kill a mole. This is just bad dad humor, so we will cross it out. Flarf. And then you just want to start thinking about it. So you want to guess what a cat mass is in kilograms. Okay, kilograms is around 2.2 pounds. How big? I don't know. Let's say to order of magnitude we have 10 kilograms, something like that. So I could then go ahead and go from kilograms to atomic mass units. And then I would want to go from atomic mass units to moles, to atoms. And the average mass of an atom in a cat, I mean, 10, 16, 12, seems to me like the average is going to be somewhere around 10 per atom. Again, this is a rough calculation. It's a guesstimate. And then you're going to do a conversion from atoms to moles. All right, so that's the type of thing. I want you to get the 10 to the something mole. Don't worry about this number. This is a where it's the order of magnitude that is important, not the actual precise number. Okay, so that's the goal of this one. All right, so we've come to the end, and I guess something I was thinking about as I was preparing these slides is that it's very easy when we're doing physics problems to think about this as a very, sort of abstract, rational space that's totally away from the world of human affairs. And to some extent, that is true. In physics, people with all sorts of political beliefs and all sorts of religious beliefs can come together and work on projects because there is something that's objective and impersonal about the topic. And I know I enjoy that about it. During college, when I was most of your age, I would do physics when I was having, relationship troubles or something like that, because it gets your mind off things. It's sort of a refuge in a cold world. But the problem with physics, I think, is that also the ideas sort of trickle down into the wider world. And so here's a little story to leave you with. This guy's name is Percy Bridgman. He, in the 1920s, became very troubled when relativity theory sort of burst into the international stage, and everyone started talking about it as a major new way of thinking about physics. It sort of shattered the ideas that everyone had a common time they could talk about, everyone had common distances they could talk about. And Einstein's stories often talk about, what you have to do to measure a distance. You have to send a light signal to one end of the meter stick. You have to send a light signal to the other end of the meter stick, and you don't know what the time and the space coordinates of it are until you establish a way of doing it. So Percy Bridgman very boring writer, but very good physicist, won a Nobel Prize for his work on high density or high pressure thermodynamics. He wrote books like The Logic of Modern Physics, where he would write these very, dogged descriptions saying, you don't know what a meter is until you come up with a method of measuring it. So he'd say, okay, what do you do when you measure a meter? I take a meter stick, I move it by, I measure, mark one end, blah, 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 blah. And so physicists in his era thought this was very interesting because his goal was to avoid something like relativity sneaking up on physicists again. You've got to secure knowledge. But what happened in physics itself is that almost as soon as he, laid out this philosophy, quantum mechanics comes on the scene, and physicists realize we don't know quite what we're doing, and we have to be a little bit more open into our interpretation of our experiments. On the other hand, after physicists had pretty much left behind a lot of the ideas of Bridgman, they stuck around, and the psychologist B.F. Skinner read them. And he thought to himself, what Bridgman's saying makes a lot of sense. Maybe all humans is a series of measurable inputs and outputs. So, stimulus response, you put in you put in a stimuli, see what kind of speech acts come out. And this approach to psychology became very popular, became a dominant approach in the mid-century. And so I'm not saying this to just beat up on Skinner, because he was a brilliant man and had some real insights. But taking methods from one field and applying them to another without some skepticism can lead you into some real problems. And I think a lot of psychologists have left behind Skinner's framework because there are a lot of things that are not just input-output sorts of you can reduce it to the numbers. So all I'll say any more on that is just you got to be a little bit careful when someone says that something they're smuggling into the real world from science is just apolitical, objective, all of that. Be a little careful. The history of the meter has a rich and varied life. So anything that's more complicated than a meter is bound to be even more complicated than that. So what are our big ideas of today? All right, after my pontificating. A, for physical quantities to be meaningful, they have to have conventional units attached. B, we can shift from one system of conventional units to another using our train tracks. You can multiply by 1 as many times as you like. And C, it's important not to misrepresent one's knowledge of a situation with scurrilous sig figs. All right, thank you for watching. Homework is not due this Monday because it's a weird week and we have Martin Luther King Day on Monday. So homework will be due at the beginning of class on Wednesday, next 1 week from today. All right, thank you and have a good week.